Hello, my name is Bradley Sakaguchi, and as you know, over the course of this last semester, we have been working on our PIP, or Personal Interest Project. And what that is exactly what it sounds like, a project time that we have to investigate whatever intrigues us. Um, may it be a new type of kazoo, if that's what you want to do, rapper. Um, but what I chose to do is solar panels, and to kind of help educate people in that technology because it is a very important technology, um, and its importance is only going to increase with our ever-growing demand for clean, renewable energy. Um, it also has, in my eyes, one of the greatest potentials for digging us out of the hole that we dug with climate change and global warming. Um, but to teach people, we have we have three essential questions that we need to answer. Um, One, how do solar panels work? What's the science behind them? Two, what's the most efficient type so that people know and can understand what's the best choice and what will be the most possible outlook for our future. Um, and three, how do we get the word out about this, and how do we teach people about this because it is important. So, for the first question, how do they work? Um, this is actually a more complicated question than one would first expect. Um, but that's what we set about doing. We set about learning about solar panels. Um, and that brings me to my first slide, which is research. And we spent a good long time um, just doing research on the technology of solar panels. Um, and I'd briefly like to explain to you the science behind solar panels because it's it's fairly interesting and important. Um, so basically, what a solar panel is made out of is one N-type silicon, or negative, and one P-type silicon, or positive, stacked on top of each other, N over P. Now, the N-type silicon is doped with phosphorus, and this phosphorus has 5 electrons in its outermost shell. Of course, the P is doped with boron, and that has 3 electrons in its outermost shell. Um, so this creates, this means that the P, or the N, wants to give some of its electrons to the P. But unfortunately, the atom does not have enough energy to make the electrons go. Um, so that brings us to how does it get that energy to allow the electrons to flow. Um, and that uses an effect called the photoelectric effect. And what this is here's the solar panel, and as you know, light is made out of waves and photons, and the higher energy photons create smaller uh, wavelengths. So that means that blue and infrared will have lower energy levels, and red and infrared will have higher energy levels. So when a when visible light hits the solar panel, it has enough. Oh, sorry. Visible light and up, so infrared also included, hits the solar panel. It it can knock an electron out. It can excite the electron enough to where it will want to. It can escape from the outermost shell, and it's a free electron. Now, this electron only has enough energy to escape. It won't go anywhere by itself. And that's where the phosphorus doped silicon and boron doped silicon come into play, because the potential between the two, the electron will want to travel, and it will choose the path of least resistance, which in this case is the metal on top. So the electron will go in through the metal, go through the collected wire, and power whatever it needs to, and come back into the boron. And there's a little separating layer between the two that will allow the electron to go back up into the phosphorus, then creating a renewable cycle. So that's basically how it works. And if you have any more questions, the time after in the Q&A, you will have plenty of time to ask me questions about the science. So that's the first thing that we did. Just research. We know how it works now, but how do we continue? We know it, but shouldn't we build one? Yeah, let's do that. Let's build one. So we ordered the parts, and through the time that was ordering, it took a bit longer than expected. So that set us back about a week. An unfortunate oversight. But we continued to research through that time, and got our understandings very good. So we decided to build a different type of solar panel, not one using conventional photovoltaics and semiconductors, but one using a photosynthesis-esque approach. And it's called a dye-sensitized solar cell, and that's what the red square thing is. So that's what it is. And one of the things that I kept feeling, and I'd like to quote Thomas Edison here. I've not failed. I've just found 10,000 ways that won't work. And this is the feeling that kept creeping up on us each and every time we tried to build this thing, because we would put the titanium dioxide layer on top of the coated glass. And by the way, I will explain how this all works later in the Q&A if you'd like. So we put the TiO2 layer on the coated glass, and we put it on a hot plate to cure it and help it stay in place. But one of the things that we didn't really guess would happen is when we put the raspberry dye onto the titanium dioxide layer, it would immediately shatter and like an eggshell, and this caused problems. As you can guess, it wouldn't stay in place. It's like trying to keep eggshells on glass. It just won't work. So we kept trying over and over, and eventually we found a method where we had to slowly drip it on from the side of a little bit undercooked, undercured TiO2 layer, and then once we had an initial layer of raspberry dye, we could then dip it inside the entire vat of raspberry dye and leave it in there to cure. And that kind of worked. And so we built a solar panel, sort of. And I'd like to explain that in my next slide, which is testing. We, of course, built this, and we need to test them and compare them to the other more, well-tested and more well-used photovoltaics. So, also, the dye-sensitized is a new technology. It just recently came up by a Norwegian electrochemist that works at UC Berkeley, and so that's where they found it out. So it is a new technology that's not been tested, and so back to the testing. we decided to test this against other photovoltaics, and as you can see with the table, um, they worked well. The photovoltaics, they worked as expected. The poly and the mono was supposed to outperform the poly, and we'd like to run some more tests on that because I'm not sure if I believe my own eyes with that. So we're gonna have to run more tests on that because the testing was the last thing that we did, and it's not. It's only one trial, only one trial. It's not three as we'd like to do. So, but one of the interesting things that we found was no matter how big you made the photovoltaic cell, the voltage or the push on the electrons would stay the same. It wouldn't increase no matter how big the solar panel was, and this is because the phosphorus doped silicon and the boron doped silicon only have a certain potential between the two, and they will only want the electron so much. So it will only push it so much, and so it's fairly stable with the voltage. There's a few fluctuations, but fairly stable. And that's one of the things that we found. But the amps could shoot through the roof depending on the light intensity, because the more light, the more it could excite the atoms and shoot up more electrons. Now, an interesting thing that we found with the dye-sensitized is that the amps was almost unreadable, but there was good voltage um, being produced, and we were wondering what was happening. And simply what it means is it could push electrons if there was any, but there isn't. Um, and that was one of the problems. And what I guess is because one of the things that we didn't do that we should have but can't, because what we need is a platinum catalyst layer, but as you know, platinum is expensive, so no platinum. And we may try and find an alternative. One of the alternatives might be graphene or very, very thin graphite, so a pencil lead. Um, and we may want to try that with another trial and test that, but we'll see. We'll see how that works. But for now, only there was only volts being produced, so the there was the potential for it. So it was producing. It just wasn't, which means the electrolyte, which was vinegar, was working fine with the TiO2 layer and the dye. So it could, but it just didn't because the sunlight wasn't um, producing enough chemical reactions. So that's how that works. So it's been a very interesting uh, testing trial. So we'd like to continue this, and we have plans that we could continue this. But I'm not saying we are, because I'd like to talk to my partner more extensively about that. And who knows? One of us may continue, and one of us may not continue. And you know, it may or may not work. So, but there is more that we can do, and you know, work to be done. Let's see how it works out. Thank you very much. I hope you enjoyed my PIP presentation. I hope it was educational, and I hope you can see the potential in this type of learning style. Thank you.